Exercise 509 is about optimization problems. So we need to use the question we've got to write an equation, or sometimes two equations, for what we need to optimize, and putting one equation into the other. We differentiate our equation and make it equal to 0 to find the local maximum or minimum. We do have to prove that it is maximum or a minimum by the first or the second derivative test. And we have to substitute it back into the equation found in step 1 to find what the maximum or minimum value is. It's also really important to check for global maximum or minimum, as this can occur. So here's an example. Find the maximum rectangular area that can be enclosed with 100 meters of fencing. So we're asked to maximize the area. Now from this we can write two equations. So we know this is our field here. It said it's a rectangular field. I'm going to call the sides X and Y. So the formula that we want to maximize is the area. So X times Y. But we've got two unknowns here. But we can use the second piece of information to find one of those unknowns and to make it into one variable. So we know there's 100 meters of fencing. So we know that 2x plus 2y would equal 100, or x plus y equals 50. So now we can rearrange this to make, let's say we'll make y the subject, it doesn't matter which one, 50 minus x, and substitute that back into the original equation. So area equals x times 50 minus x. I'll just expand that out. It's much easier to differentiate it if it's expanded. Okay, so that's our equation that we have to minimize, the equation for area. So let's do it. So differentiate. Now just the important thing here, x couldn't possibly be more than 50 because two of them. If y was 0, x would be 50. So we do have a domain that limits our x up to being 50. That would come up if we got a value that was below 0 or bigger than 50. Then perhaps the answer would be a global maximum or minimum. So let's differentiate. So we get 50 minus 2x, and we need to make that equal to 0 to find out where it is at a maximum. Add the 2x, I'll just flip around as well, so 2x equals 50, x equals 25. Okay, we have to find the maximum area. So we do need to know what the area is. So let's find our y. So y equals 50 minus our x, which is also 25. And that's what you'll find here. If you're doing just a standard rectangle, the maximum area will be a square. So the area equals 25 squared, which is 625 meters squared. Now, I haven't guaranteed that that is a maximum. I do need to check that. I'll do that with the second derivative test. So the second derivative of our area is -2, which is less than 0, so it's like a sad parabola, so it is a maximum. So the answer is 625 meters squared is the maximum area. Example 2 is a very similar example. This time though, the paddock has been built against an existing wall, so the fencing only needs to cover 3 sides. So let's call that side X and that side Y. It's exactly the same. But this time we're asked to find the dimensions of this paddock rather than the area. So we know that our 100 meters is X plus 2Y. I'm going to make X the subject there, so I'm taking the 2Y over the other side. So X is 100 minus 2Y. Our area again is just X times Y. So I'm going to substitute this instead of our X. So 100 minus 2y times y, expand it out. So 100y minus 2y squared. Okay, so that's our formula that we need to maximize. Again, it's very similar to example 1. So we do need to differentiate. So 100 minus 4y. I might just do the second derivative while I'm at it, which is -4. So we will be finding a maximum, because that's always less than 0. It's like a sad parabola always. Okay, so to maximize, we find where the derivative is equal to 0. And that happens when y equals 25. 4 times 25 is 100, 100 minus 100 is 0. We were asked to find the dimensions, so we need to find x as well. So 100 minus 2 times 25, 100 minus 50 is 50. So those are the dimensions. We've proved it's a maximum.